In this class, we will discuss how to organize quantitative data. The idea to organize quantitative data is to convert them to qualitative data by grouping. Firstly, we will group observations into classes. Sometimes it is also called categories or bins. Then, we treat the classes as the distinct values of quantitative data. When grouping observations into classes, we need to make sure that the number of classes is not too small or not too large. If the number of classes is too small, we may miss some important features of the data. If the number of classes is too large, there may be too much information to be presented efficiently. Usually, the number of classes is selected somewhere between 5 and 20. When we assign observations to classes, we need to make sure that each of them must belong to one and only one class. It means that one observation cannot be assigned to two classes, and we do not miss any observation. Whenever possible, all classes should have the same width. There are different ways to group observations into categories. The first one is single value grouping. It is for discrete data with only a small number of distinct values. We essentially treat each value as a distinct class. The second one is a limit grouping. It is for data of whole numbers and too many distinct values for single value grouping. The last one is cut point grouping. It is for continuous data expressed with decimals. We will show one example for each group method in a while. After grouping observations, we will usually draw a histogram. A histogram displays the classes of the quantitative data on a horizontal axis and the frequencies of those classes on a vertical axis. Sometimes, instead of frequencies, we may also use relative frequencies or percentages. The steps below explain how to draw a histogram. Firstly, we need to obtain a frequency distribution of the data. It can also be a relative frequency distribution if you want to draw a relative frequency histogram. Then, draw a horizontal axis on which to place the bars and a vertical axis on which to display the frequency or relative frequency. For each class, construct a vertical bar whose height equals the frequency or relative frequency of the class. Last, label the bars with classes. Let's look at an example. The data contains the numbers of TV sets per household for 50 randomly selected households. Look at these numbers. We will notice that there are only a limited number of values. The smallest is 0 and the largest is 6. It is a perfect choice for single value grouping. Count the number of zeros, number of ones, and so on. We thus construct a table for frequencies. Divide each frequency by 50. We get relative frequencies. Make sure to check that the sum of relative frequencies is 1. The left graph is the frequency histogram, and the right plot is relative frequency histogram. The two histograms are essentially the same, and the only difference is the meaning of the vertical axis. From the graphs, we can see that the majority of households have 1, 2, or 3 TV sets. Only a few households have smaller or more TV sets. In this example, the data are numbers of days to maturity for 40 short-term investments. Most values are different from each other. Hence, it is not appropriate to use single-value grouping. We can use limit grouping here. The values are integers. We can group them into tens. such as 30 to 39, 40 to 49, and so on. Each class includes 10 possible values. After determining how to group, we then count the number of values falling into each class. Next, we calculate the relative frequencies by dividing frequencies by 40. This slide shows the corresponding frequency histogram and the relative frequency histogram. We can see that the majority days fall somewhere around 60 or 70. This is another example. There are the weights in pounds of a sample of young men. This is an example for cut point grouping. All numbers are decimals. We need first decide how many groups we need and then decide where the cut points will be. The smallest number is 129.2 and the largest number is 278.8. Use two whole numbers to include them. We may choose 120 and 280. And decide to cut this range into small intervals of length 20 each. Notice that each class includes its lower cut point but not the upper cut point. Next, we may count the number of values falling into each class. The relative frequencies are obtained by dividing frequencies by 37. Notice that the sum of relative frequencies is not 1, it is 0.999. It is essentially due to rounding error. It happens in practice. Look at the histograms. The first one is for frequencies and the next one is for relative frequencies. We can see that the weights are in the range of 120 to 280. There is one value far away from the remaining values. It is called an outlier. We will mention what is an outlier in more detail later. A histogram displays the values by grouping. We cannot find the raw data by looking at a histogram. However, a dot plot is different. It preserves all the original values. A dot plot is a graph in which each observation is plotted as a dot at an appropriate place above a horizontal axis. Observations having equal values are stacked vertically. In this example, the numbers are 16 quotes on different brands and styles of DVD players. To draw a dot plot, we first need a number line. For each number, mark a dot at the corresponding location. If we have repeated numbers, stack them vertically. For example, we have three values of 199. In the dot plot, we have three dots stacked vertically. The major difference between a dot plot and a histogram is that we can get the exact values of the original data in a dot plot, but we cannot in a histogram, which only gives a summary. A stem and a leaf diagram or stem plot is a different way to show raw data. In a stem and a leaf diagram, each observation is separated into two parts, namely a stem and a leaf. A stem consists of all but the rightmost digit, while a leaf only consists the rightmost digit. In this example, the numbers are the number of days to maturity for 40 short-term investments. The right shows the corresponding stem and leaf diagram. Let's see how to read a stem and leaf diagram. A vertical line in the center separates stems from leaves. The stems contain the first digit and the leaves contain the last digit. For example, the first row is stem 3 and leaves 6, 8, 9. It indicates three numbers, 36, 38, and 39. Yes, each leaf corresponds to one value in the original data. Let's check the bottom row. It has stem 9 and leaves 5, 8, 9, 9. It indicates values 95, 98, 99, and 99. Similar to a dot plot, we can extract all values in the original data from a stem and leaf diagram. Another way to look at the stem and leaf diagram is to rotate the table by 90 degrees. It looks like a histogram. The more numbers in a stem, the more leaves, and the higher the bar. In this sense, we may say that a stem and leaf diagram is a histogram by symbols. Let's see how to construct a stem and leaf diagram. First, partition each numbers as a stem and a leaf. Then, write the stem from smallest to largest in a vertical column to the left of a vertical line. Write each leaf to the right of the vertical line in the row that contains the appropriate stem. Last, arrange the leaves in each row in ascending order. This is another example of stem and leaf diagrams. A pediatrician tested the cholesterol levels of 20 young patients. Look at the values. Each value has 3 digits. We may use the first 2 digits as stems and the last digit as leaves. So there are 3 possible stems, namely 19, 20, 21, and 22. After completing the stem and leaf diagrams, we may notice that the diagram is short and wide. We have only 4 stems here. It is similar to how to choose the number of beans in a histogram. It is not good to have too small number of beans. In this case, we may partition each stem into 2 stems. For example, we have 2 19 stems in the right stem and leaf diagram. The first stem contains leaves 0 to 4, and the second stem contains leaves from 5 to 9. Similarly for other stems.